I'll take just a few minutes to introduce our topic today and offer some thoughts on the future of distance learning, share a little bit about Automation Studio's powerful simulation software for hydraulics, pneumatics, electrical systems, and PLCs. That will go quick because I want to leave plenty of time for the guest who's joining us. In just a few minutes, you'll be hearing from a Wisconsin Technical College program director who's going to demonstrate how he uses Automation Studio to create outstanding learning experiences for his students. So let's get started. Why is today's topic so important? Why is it crucial that we explore options for virtual learning on a platform that comes as close to reality as possible while enabling our students to learn, experience, design, practice, and troubleshoot remotely? I think in this era, we all know the answer to that question. But the first point I want to make is that manufacturing and the demand for your students is not going away. If you were one of the more than 100 people that were able to join us for the Lunch and Learn series that we hosted on Friday, we heard from a former Navy SEAL Team 2 commander who is now the CEO of a major manufacturing company, and he said this: "I actually think the future of advanced manufacturing is incredibly bright. I think we will continue to see a questioning of the status quo global supply chain now that one can see the impacts when it gets disrupted." Just a reminder that our manufacturing sector will be stronger than ever before come the end of the current crisis. Any lull in manufacturing orders will be temporary, and when we are back to full production, the demand for technical talent will be greater than ever. The demand for your students isn't going away, it is growing, and that is great news for those of us who serve in the field of technical education. But the way that we train, educate, and offer interactive experiences to our students will change, perhaps forever. Last week, our team published an article on how institutions of higher education are managing through the current crisis. We'll share it via email with all of our attendees following this webinar, but listen to these comments. This from the provost of the University of Wisconsin-Milwaukee, Johannes Spritz, who says, "The current crisis is accelerating the general transition to digital learning, and this transition will continue. He foresees an increase in online teaching as institutions of higher education move to hybrid models and integrate in-person instruction with experiential learning and online content delivery and simulation also playing a significant role." Or this from the CEO of Gateway Technical College, who says, "We are preparing to deliver at least 50% of our curriculum online in the fall, and we will make the investments necessary to do so in a way that maximizes the student experience." And just as a reminder that distance learning is so much more than a Zoom meeting or a YouTube video, the former Deputy Assistant Commissioner of Workforce in the Division of Workforce, Academic Affairs, and Research at the Texas Higher Education Coordinating Board, Gary Tomerlin, shared this: "You can't just take a 48-hour contact course, slice it into 2 or 3 minute videos, and assign them to the students. If I was a student and you told me my assignment for the next 3 weeks was to watch 900 videos, I think I would drop the course." Now, don't get me wrong, hands-on learning in our labs will still take place. We still need to get students working and learning on authentic equipment. But our path there and the balance between hands-on and virtual will put an increased emphasis on effective virtual learning tools. It has to. We will have 2 types of teachers, instructors, and professors: those that embrace virtual learning as a tool to support their programs, and those who refuse to change and simply wait for the new world of virtual authentic fusion to go back to the old world of learning. In my opinion, the future is not bright for the second group of people. And Lab Midwest is adapting too. This week, our entire team will complete our 7-week journey through the virtual curriculum that is prepared for us to sit for the SACA Certified Industry 4.0 Associate 1 credential. Our entire team, including our accounting, marketing, and administrative people. And that's just the beginning. Our business development team, located throughout 7 Midwestern states, is becoming even more adept at supporting our customers as they move more and more of their content to a virtual environment. We launched our new product, Interactive, that enables our tech service team to use augmented reality via our customers' smartphones to provide technical services to see exactly what they are seeing and coach them through solutions virtually if social distancing prevents us from entering their facilities. We now have 2 full-time virtual learning support specialists that coach our customers through setting up and maintaining virtual learning systems. And we offer them now for almost every discipline, from welding to fluid power to hybrid vehicles, biomedical, mechanical design, controls, and the list goes on. We are ready for the new world of technical education. One of the solutions in which our partners have shown the most interest is Automation Studio by Famic Technologies, and dozens of our customers are already using this powerful tool. As we loop some video for you, let me ask some questions. In this new era of virtual authentic fusion, where we begin to blur the lines between simulation and hands-on skills, what if there was a way to simulate our lab experiences? What if we could pull electrical, fluid power, and controls components from a virtually infinite library of authentic industrial technology? What if that tool was so powerful that we could clone the equipment that sits in our labs today, not choose someone else's equipment, but provide perfect digital simulations of what is in our labs now? What if our students could build a circuit, either one that we designed for them or one that they design on their own, and do it from the relative safety of their own homes? What if we could then activate that circuit and see it come to life, actually see flow circulating through it? What if we could combine electrofluid power, electrical technology, and controls technology into one multi-technology circuit design and simulation? What if we could insert or create links to our own documents or directly to outside websites, videos, and information that can support or explain the system? And what if we could create voiceover audio files that could shepherd a student through the circuit, explaining it along the way, addressing our auditory learners, our visual learners, and our kinesthetic learners all at once? Automation Studio does all of these, and that's just scratching the surface. Joining me today is my friend, Tim Tewalt. Tim is a world-class educator and innovator who is viewed nationally as an early adopter of flipped classroom technologies. As well, if not better than anyone, Tim combines the power, flexibility, efficiency, and student-led nature of virtual learning with the personal direct demonstration, coaching, mentoring, hands-on experiences, and career inspiration that takes place in his lab. He's an educator, he's a web developer, he's even served as a city council member in the city where he lives. Tim is the program director of the Industrial Mechanical Technician program at Chippewa Valley Technical College in Eau Claire, Wisconsin. And Tim, we are so glad that you're able to join us this afternoon.
Thank you, Matt. And it's always humbling to be with peers, and I'm excited to share what we're doing and start a dialogue to continue to learn.
And I know our audience shares that excitement as well, Tim. Tell us just a little bit, if you would, what we plan to see in your presentation today.
You know, as we hit this COVID-19, we had already been starting to be entrenched in virtual things such as e-learning, et cetera. And we had to solve some problems that, how do we do troubleshooting? How do we make them see the things we really can't even see in lab and fully understand it? And we've been using Automation Studio and some other tools to fill in those things. And so here I've put together 4 different snippets of what we've been doing. We also use this where a student will create something, they will record and give it back to us, a screencast showing they understand what this does. So it's a very dynamic instrument, both for the instruction and both for the learning and assessment of.
Perfect. So should we dive into some of the videos that you have here and have you share with our audience what it is that they show?
Yeah, that'd be great. So,
all right. So here's number 1.
Yeah, the first one, you see a forward reverse motor circuit. It has typical overloads, that type of thing. A funny 5-switch fault panel there. And those faults are underneath are listed 1 through 5. The student wouldn't see there. Up on top, we've got multimeter, amp meters, and we run this thing. So the student's able to observe what it looks like when it's working. They can take measurements. They can activate it as I'm doing right here, and they can see that the motor goes. It's spinning. I haven't put a inertial load, so this motor is real. It's going to coast down. It's not going to stop immediately. And I can reverse it, and we can see now that arrow underneath it. So this way they're learning, you know, oh, it was the R2 contactor that made it go reverse. And what if I do this? What if I hit the stop switch? Because we start with knowing knowns. we usually start with something like, well, what would your first checks be? Well, here we can go out. We'll see if we're actually getting power. The 19.98, it's a real system. It knows about those little things aren't perfect. It knows resistance of wire and all sorts of things. So here I've got the clamp meter on one of the phases. I'm going to start it up, and we're going to see what that looks like as it runs. If you watch the current meter over on the right-hand side, when I start it, we're at 67 amps. Big inrush current on a 10 amp motor, 12 amp overload. But now we see it's running about 9.3 and we see normal operation. The students are given this file. You don't have to build it as elaborate as this with the fault switches. But now that they've seen how it works, they're going to activate one of the faults. I even left the instructions in red up there what they do. They activate it. That's just coasting motion. It wasn't going. It won't go in reverse or forward. And that maybe starts them on a journey of, gee, what should I measure? Well, after some observations, we teach a troubleshooting process. They're going to go verify, I wonder if that stop switch is good. They verified that just like you would in a lab. Maybe they want to go kind of in the middle and activate that. And they go there and see that's the reading. And it's kind of fun. I had one student tell me 5 millivolts was good. And that's what they do in the lab, how to interpret readings. And when they send back their recording, I'm able to look at it. So in this one, it's not working. Here's a fun reading that is an indication what's wrong. Boy, how did we get 120 when the load should have dropped it at all? And if electricity isn't your thing, these are the same checks we do mechanically, etc. Here, I'll just remove it as this is for this purpose. And we see we can't measure on the 0 or the ground line or the neutral line, whatever you like to call it, on the return, unless you are referenced off the hot side. Now we see, sure enough, we get our 119. We know the wire from the transformer going to the right is good. And now I put the fault back in. We go here, nothing wrong with the overload. We go here, we don't have any voltage. That wire is broken. So they can unpower if they want. They can actually break the wire. There's some buttons you're going to see up on, you won't see up on top that'll be activated to be able to break the wire, take the system off. It's actually still in simulation. And they're just applying this little break wire tool. I'm able to open the wire and decide wherever I want to put it that there's a break. And now I can use an ohm meter and see what it goes. The 5 different bugs are typical ones. Trying to do a broke wire, trying to do a high resistive wire, a burnt out transformer where maybe the secondary's been blowing the fuse or it's shorted to the core. Those are hard to put in a lab and swap out a good transformer and a bad transformer in between students. On this one, we can do it. So we can also jam the rotor where the bearing's bad. Again, very hard to do in lab. And here the student verifies, hey, I see the issue. That wire measures 0 ohms with the fault gone. Again, the fault could be hidden. It could just be a file they receive. So these 5 circuits or problems, they each had to troubleshoot, give me a synopsis that explained how they found it, as well as fill out a troubleshooting maintenance report that we follow a standard pedagogy. So this one is just showing that here, when we start it, it helps if you give it power, hit forward, and we're going to see, boy, this one's the transformer's blown, and again, the troubleshooting. So these are the main type of things I did with this, Matt, to be able to give students realistic bugs, things we practice in lab, and some we've learned this does even better.
Outstanding. Well, and I love the idea, Tim, that you're able to take this and then send it back to, have the student actually do a video of their process of identifying the fault and sending it back to you, especially in this era of virtual learning. I imagine that's got to be tremendously effective.
There is, and there's certainly screen capture tools, but built into Automation Studio, you can also do the recording.
Outstanding.
So it really fits a lot of flexibility.
I love it. Shall we move on to your hydraulics example?
Yeah, let's go to that one.
All right.
The This one, I did a little fast motion of it, prototyping together. That's not really me. That's me using the video editing to do that, Camtasia. But look how easy the connections are. I click. I can move things. I can double click, make a union, put it in. I can route wires or conduits, conductors where I want. And I'm simulating. That's just how easy this software can be. If you wish to describe the cylinder, its diameter, its length, you can make it identical to your lab equipment. Here I'm going to take this one where we're going to rotate this at 45 degrees. And again, this is just showing you what can be done. So don't try and follow this as steps. And I'm putting 5,000 pounds, call it a small little log splitter. I mean, normally we'd go like 28,000 if we're doing oak or something, but we're going to see that this moves. Now, when I activate it, I'm putting a pressure gauge there. We can see the amount of work and the flow. The key is that it's going to be something to see how does it really work, because we're going to see the cylinder will activate, the one with 5,000 pounds will lag, which you might expect. Sorry for a little bit of jumping here, but that'll settle down in a moment. And sure enough, we see it there, we put some pressure on it, and then when we activate it, we'll see it will actually go out. I'm just going to wait for that to come up in the simulation. We're running recordings because we wanted to make a smooth path for no delays in it. Here's a side benefit. I can copy and paste that. It's a vector diagram, goes into Word. Very nice feature. I can make a quiz where I ask students to identify these things. So different things. Hey, here's a plotter. Very complex to use. I drag the component onto it. I say I want to know its speed or position. And now it's graphing what's going on. You can go back and look at it with the cursor. You can scale it, see all these sort of things. And if you look at the green, that's that pressure when you slam a cylinder one way or a valve the other way. And we're not going to talk about it here, but the students, you can really have talks with how things work. It's very key that they actually get to think how things work. So this looks like it's repeating right here, Matt.
Yep. Yeah, we just have it looping to make sure that you can make all your points with the video on the screen. But
these are things we couldn't show in lab. Students nod that they understand it. It's like they nod when you say back pressure, or is that just pressure? Well, if the pressure's on the left side, is that back or forwards? I'm using that a little bit jokingly, but being able to see it is just huge.
Absolutely. I remember, Tim, when you showed me that plotter example, I think that was the one that of all the things that you're doing with Automation Studio really caught my attention and really generated the understanding of the power of the solution that we're talking about here today. That and the ability to pick and place items right out of the schematic and put them into a Word document has to be great for creating programs and for providing instructions to your students.
Yeah. And now this is a response to a student having a problem with solenoids. And when I worked at Cray Supercomputer, we didn't have any schematics. They didn't use any. They used Boolean equations, modified, if you will. And we know things are solenoid valve, but a solenoid, is that to open a cash register drawer? Is that relay on a car that they used to call a solenoid, which was really a relay on the starter? So here I've used Automation Studio. The student is familiar with what's on the left. They've been doing pneumatics. They've seen that. They've operated the, here we're going to go into simulation. Right now I'm going to operate it just manually, where I hit that manual operator, or the check mark means I've just forced it in that position. Here I've used the actuator itself, be it a foot or level, and the students see it moves. What's funny about our nomenclature is the solenoid, as most know, that's that little slash that it points to, that little rectangle with a diagonal through it. But that's not a valve, that's the operator of the valve. And again, we get students agreeing to things and not knowing. So as they ran into problems with that, here's what the electrical world says. It's this little zigzag thing, kind of like a resistor that gave up after the first hill. is the schematic symbol. And they're to know that's actually a solenoid, which is actually the same as the thing, or looks like this in that diagram from a manufacturer. Well, in the middle, here we've got the electrical circuit. You see it's activating the pneumatic. And if you look closely, I've put the image of a valve, and you can even see the green LED lighting on that I can now feature, hey, here's the spring part. Here's the manual operator that we were just referencing. So they can connect schematic to physical all in one setting, not 2 weeks later in a lab. And we wonder why they didn't pay attention. The spring, this thing's the solenoid, not the thing that gets the wire. What wires? Well, these little wires that have to, be connected that are coming to a terminal strip. And I could have detailed all that, but this was just to help a student understand. And then we became part of our learning, and we can add quizzes on this, that this is what we mean when we say a pneumatic valve that's electrically actuated. Otherwise, we just say, well, yeah, get a valve with a solenoid, or get a solenoid valve. So long titles, little slogans that are little common industry phrases. We short, everything's a prox, doesn't matter what it is, switch, magnetic, photo. We blur that language. That is common, but in the learning, it makes it really tough. I don't want to leave them just at that. I then will be seeing coming up, I established the LED function, but down below, it's going to go to the video. It's going to show just some other applications of solenoids, because as you know, they're used in all sorts of places. So I'll zoom out here, and we can see we've got those that are used in some sort of plumbing, some sort of fluid control, whether it opens or closes, bypasses. Same way with the next two ones, that they get to see some physical components. So yes, a solenoid is an electromagnetic device. It is either AC or DC. It makes a pull-in action, but the spring return, the application is much more. And what a great way to help that. And the clarity went way up, and now they recognize it in other places.
It's just a great example, Tim, of the ability to take a virtual learning environment and tie it into the physical manifestation. One of the biggest challenges, I think, in virtual learning is making sure that the student is grasping how what they're seeing on the schematic or on the virtual end ties to the physical asset within the manufacturing environment. And I think you've done just a phenomenal job of demonstrating that. We have one more example, I understand, understanding DVM readings.
Yep, let me just pause before you go on there. I just want to emphasize, I want to add one point to yours, Matt. It's also extremely hard in the lab.
Right.
Yes, the students who are catching it right away nod, but many don't get to see what we just went through.
Absolutely. Great example.
And they get C's or D's, so I guess they're not gifted. Right. I'd say that tongue in cheek. So this way they get to see it and ask their questions of the learning. So this last one was very similar. The yellow boxes are test points that Automation Studio allows you to apply as many as you want. We had problems with students understanding measuring from a positive reference or a negative reference. They called everything ground, and they called wires. Everything was a short. They thought the switch might have a short in it. I have no idea what that meant, because I know the correct understanding. So here we were able to show them as things open and close, what the meters would read, what the light would do, that thing with the red, and what happens if I decide to short the load. And that's going to cause excessive current. Instead of 1 amp, we're going to see it goes way up and the fuse blows. And that is a really key thing. And now what do the voltages look like when we have an open in the circuit? So that was really key to understanding that little part of that, being able to really understand what readings mean. They tend to sometimes start with a meter and just go crazy of measuring all over and from what reference point they don't know. So this is a narrated video that they go through, and then I ask them some questions. Again, after I've done this, I can then give them this circuit, have them rebuild it. And here, this one I've modified a little bit. I've got that fault switch that I added, and I'm going to make the bulb go bad. I'm going to burn it open. Sounds simple, but students think the bad bulb should have 0 volts, not the source. Here, they're going to get to see that even when I blow up the bulb, it's not going to result in that. I don't think you're going to catch the yellow readings live, Matt, because I did speed it up to go through.
Yep.
But again, hey, they've been watching that. Now they're going to pull out the physical meter and see for themselves. Oh yeah, I got 24. Oh, I get 24 through the switch. I get it. I go here. Oh, I got 30 volts. No, 3 millivolts. That doesn't, I was looking for, etc. So this is a really thing that was hard for students to grasp. People say electricity is abstract, and I asked them to tell me where the hydraulic droplets are going. We can't see them either. They're just inside the hose. So having tools to visualize, having tools to show the relations, this automation studio has just been really helpful, both in regular lab session and virtual. The key of automation studio to understand, it is, to use their lingo, a full PSpice simulator. This is doing simulation of wire resistance. You can put in the length of the wire if you want. You can see what that's going to be. I went to hydraulic training on it, and the folks at Parker, for example, or Eaton, they go for I think it was full month. So when they build a big cat, they don't want to find out it doesn't work.
Right.
So it's a very simple to use tool, as we saw. Here's a voltmeter, here's an ohm meter, see if a light bulb turns on, to very complete models. That really adds to understanding of things you just could never build.
Great example.
Within a semester.
Absolutely. It's a perfect example. Outstanding. Well, just great examples and a great presentation, Tim.